Thanks so much for coming by to hear the talks today. So we decided to break things up with two speakers. So in the first half, I'm going to be covering the biophysics underlying neuromodulation, and then Z is going to talk about the physics behind the latest technologies in the field. So there's four main points I'm going to cover. I'm going to start by talking about I'm going to start by talking about how we can use technology to introduce energy into the brain that can modulate neuronal function, neuromodulation. Then I'm going to go into, once that energy is in the brain, how are neurons responding? And the last 2 points are going to involve modulating the stimulator settings to probe the brain with specificity at the level of different cortical layers and even different neuronal receptors. Okay, here's a fairly straightforward cartoon of TMS. So this gray bar, transcranial magnetic stimulation is what TMS stands for. This gray bar is the TMS coil. And this lightning bolt represents the neurons here in motor cortex responding to the stimulation. And it's motor cortex, you have this long corticospinal tract axon, the synapses at the spinal cord. Stop doing that. And we could record using electrodes at the hand, a technique called electromyography, this wave known as the motor evoked potential, which occurs about 20 milliseconds after the TMS pulse, which is the latency for information to travel down this pathway. So zooming in a little bit, these two circles represent that magnetic field that is created when a high current is passed through the TMS coil. Wow. And this circle here is the electric field that is created by the magnetic field. So here's a picture of one of the most commonly used TMS coils. It's called the figure of 8 coil because it consists of two wires positioned two coils positioned side by side. And it's very useful because the current in the side-by-side loops flow in the same direction in the middle. So the coil can be summarized or simplified by thinking of it as a vector of current in a single direction that it can be positioned now in three-dimensional space and pointed in different directions. And we could determine the magnetic field produced by this current vector, by using the Biot-Savart law, or which is known as the right-hand rule. So if you point your right-hand thumb in the direction of current going in a wire, or in this case, this current vector, your fingers will curl around in the direction of the magnetic field produced. So this magnetic field sort of propagates deeper into the brain, away from the wire. And the strength of the magnetic field produced is on the order of 1.5 to 2 Teslas. So this is a fMRI course. So by now, we've all learned that this is the strength able to use to image the brain, right? And so you might ask yourself, well, so when I enter a 3 Tesla or 7 Tesla field, are our subjects' brains being stimulated? And the answer is no, because of this equation, which was the Maxwell-Faraday equation, which tells us epsilon, the electromotive force, which is a fancy term for voltage, is governed by the d phi b over dt, which is the rate of change of the magnetic field. And here's a graph of the coil current, which is the same as the magnetic field exactly follows this waveform. And you can see it's very fast. It's over in about 500 microseconds, half a millisecond. And the rate of change is the derivative of this waveform. So here's that. So this is the waveform induced in the brain. And where there's voltage, there's currents. And so this negative sign is Lenz's contribution to this equation, and that tells us that the currents are generated in the opposite direction as the currents flowing in the coil, essentially. Okay, that should be right in there. So there's this chain of events currents in the coil create a magnetic field, which in turn create an electric field in the brain. An electric field is another way of saying voltage or current. So I'm going to use those interchangeably, but electric field is, I prefer as the best way to summarize how much stimulation has gotten into the brain. And Z is going to talk about that in greater detail as well. So another way to create an electric field in the brain is by implanting deep brain stimulating electrode, as shown in this X-ray here. And people will use the term virtual electrodes to describe the voltages created in the brain. And there's a positive source and a negative sink, just like there are with DBS. Now, we lose some focality by using this magnetic coil outside of the brain, but the trade-off is we don't need to have invasive surgery to produce the currents in the brain, and that trade-off is very favorable for the utility of TMS, having an increase in popularity over the years. Similarly, transcranial direct current stimulation also uses electrodes. To make it a little confusing, that field tends to use the term anode for the positive electrode and cathode for the negative electrode. Those terms come from the materials used to make up batteries, these two colors representing the anode and the cathode, and the current flowing from the anode to the cathode, positive to negative. And so transcranial direct current stimulation is even less focal than TMS. And it's the amount of current that gets into the brain is much, much less, so small that TDCS is thought to be a sub-threshold form of neuromodulation, where we're not actually causing action potentials into targeted neurons, where TMS, we do think we're evoking action potentials, and we're getting this output of the brain systems, such as the motor evoked potential. So I'm throwing around this term electric field, so let's unpack this for a moment. So I already talked about how there's a positive and negative virtual electrode for TMS, or real electrodes for TDCS, and they create currents, they create a voltage, and where there's a voltage, according to Ohm's law, which is this equation here, where there's a voltage, there's a current that's scaled by the resistance. So the resistance in this case is the resistance of this large medium of the brain. And the voltage is a gradient that goes from most positive at the positive electrode and scales to most negative at the negative electrode. So a voltage is a measurement between 2 points. And the largest points would be from one electrode to the other. But as we make the size of our measurement smaller and smaller, we'll record smaller and smaller voltages. So the electric field is really simply just normalizing this distance by a certain distance. So typically it's described volts per meter, but you might also see in the literature volts per centimeter or millivolts per millimeter. So essentially it's the first spatial derivative of voltage. And that's going to be important when we talk about how neurons are responding to the stimulation. So now that we've discussed a little bit of how the energy is getting into the brain, I'm going to talk about how we think it's the terminations and bends at axons that are most likely to be responding by this energy. So I talked about the electric field, which is the first spatial derivative of the voltage. Okay, sorry about all the clicking. So the electric field is the first spatial derivative of the voltage, and the activating function actually is what's going to predict how the neuron is going to respond. And that's the second spatial derivative of the voltage, which makes it the first spatial derivative of the electric field. It's in the units of volts per meter squared, or volts per meter, which is electric field, per meter. And that's important because it's telling us that the largest depolarization occurs where there's a high degree of bending of the neuronal membrane with relation to the electric field. So either the electric field can bend or the membrane could bend in a static electric field. And that occurs very commonly in the brain where the white matter bends, where the axons bend out of the white matter to innervate cortex. So TMS is so the first thing that this is telling us is that TMS is primarily targeting cortical structures, and it's not really thought to stimulate deep brain structures below the white matter. So we have this this image of how currents are created in the brain, and there's a voltage, there's positive and negative virtual electrodes or real electrodes for TDCS, and a voltage gradient across them, right? So let's take that gradient and imagine that there's an axon. So here I'm translating the gradient here along a theoretical infinitely long axon that's perfectly straight, okay? And we have this voltage gradient that happens to be going 30, 20, and 10, and these red arrows indicate that these measurements of voltages are across equally length spaces. These red arrows are the same distance apart. So if we take the first spatial derivative of these voltages, that's the electric field, and we get units of 10. 30 minus 20 is 10. And if we take the second spatial derivative, or the spatial derivative, first derivative of the electric field, 10 minus 10 is equal to 0. So the activating function, the second spatial derivative in this theoretical, hypothetical, perfect example is 0. So we could translate this to a circuit and use Kirchhoff's current law. So we talked about Ohm's law, V equals IR, which tells us that if these resistances, extracellular resistances, R2 and R1, are the same, then, and the voltages are the same, drops of 10, then the currents are going to be the same. These green arrows represent the same amount of current passing across these extracellular resistance, these segments along the extracellular space along the axon. So Kirchhoff's current law tells us basically says the current flowing into a node, which is this point B right here, has to be equal to the current flowing out of the node. So because the voltages created the identical currents across R1 and R2, that means there's no current left over to be sourced across R3, which is the transmembrane resistance. And current going across the membrane leads to depolarization. So in this perfect case, no matter how much we increase the stimulation, if it was 300, 210 voltages, we'd still have 0 current going into the neuron, okay? But as soon as we introduce a bend into the axon, now along this segment of distance along the membrane, we have a drop of 10, but this same segment now, it stops at 11, so the drop is 9. Now let's translate that to our Kirchhoff's current law equivalent view of the circuit, and we have this electric field, first spatial derivative of 10 and 9, which leaves us with an activating function of 1, the difference between 10 and 9. And so that means that the resistance here across R2 is going to be greater than the resistance across R1, which leaves current left over to be sunk into the neuron. So now with this bend in the axon, we've resulted in stimulation and potentially action potentials if that current is large enough to cross the action potential threshold. And this has been borne out experimentally. So investigators have taken a long sheep phrenic nerve and bent it by increasing degrees, and as the degrees increase, so does the resulting neuronal response here, with 90 being the greatest response at a right angle of the bend. And this is important because what it's now the take-home message for all of this is that orientation of the coil matters. So here, a group used tractography and used 3 different coil orientations in relation to the tractography, and you can see that the resulting activating function is greatest in this example at a 90-degree coil orientation. So perpendicular. So the kind of rule of thumb that we use is going perpendicular to a sulcus, because that's where the bends are going to be, and you'll align the electric field to those bends appropriately. And that's very useful. Z's going to talk about neuronavigation later, where we could exactly see where the sulci are. We can't. It's very difficult to use tractography and get to this level of detail, but using the sulci is very, very feasible. And in fact, with motor cortex, we just sometimes, if you don't even have that, you just say 45 degrees from the midline, because you know that the sulcus is going to be perpendicular in that direction. And a termination of an axon or a synapse can be thought of just as an extreme bend. So we have 30, 20, and 20 voltages. So I'll translate them to this equivalent current law. I'm sort of straightening out the bend there, the termination. And you can see that all the current that goes across R2, there's none across R1 in this example, because there's 20 and 20 is a electric field of 0. There's no voltage gradient here. So all the current gets sunk right into the axon, leading to a particularly high hotspot of stimulation for the synapses. In fact, a fairly simple model of cortex here simulated a TMS response just by activating all synapses at once, and they were able to reproduce many of the basic physiological effects seen in TMS in humans in the clinic. Okay, so now I'm going to move on and talk about how we can modulate the parameters of the stimulation to get specificity, first at the level of cortical layers. So we have this picture in our heads how the stimulator produces an electric field in cortex. But now if I increase the stimulator output, increase the amplitude, now the electric field stimulates stronger, but also deeper, but it's less focal. Okay, so there's a trade-off there. So a low-intensity TMS pulse, what we think is happening is we're stimulating these white matter afferents going into cortex, and they're innervating this simple model of three parameter model of cortex. They're innervating the layer 2-3 pyramidal neurons and also the GABAergic network. And of course, cortex doesn't look like that. It's much more complicated, but here are the layers 1, 2, 3, 4, 5. And now if we increase, so the best evidence that we're stimulating these afferents is that if we record at the spinal cord using epidural spinal cord recordings, we see these I waves, which are also known as, which stands for indirect waves. And the latency of these are such that it necessitates that there's one or more synapses involved to get the information down to where we're recording at the spinal cord. So it has to go through some of these synapses of this network before it goes out of these layer 5 neurons are the ones that innervate the corticospinal tract. Now, if we increase the stimulator output, now we think we're stimulating the corticospinal tract directly. And now our epidural spinal cord recordings show a new wave called a D wave, standing for direct wave. And the latency of this necessitates that no synapses are involved. And as we sweep the stimulator intensity from very low to very high, we see this characteristic sigmoidal shape of the MEP response, the amplitude that we're recording at the hand muscles. And there's a couple interesting parameters here. The plateau of this curve, this curve plateaus because this represents we're stimulating all of the cortical representation of the muscle we're recording from. And there's another important parameter we can derive here, and that's the motor threshold. So below this stimulator output, motor threshold, we record no MEPs at the hand muscle. And this is, you'll hear this term motor threshold because it's used to dose whenever you want to take your TMS outside of motor cortex to a piece of cortex that doesn't have a readily measurable output. Stimulating as a percentage of motor threshold allows you to translate and normalize to that subject's individual anatomy. So like the thickness of their skull tells you how, it governs how far away the stimulator coil is to their brain. And so that's basically fairly normalized between motor cortex, where we have a number to work with, and prefrontal cortex, say if we want to treat depression with TMS. So you'll hear that as a very important parameter for dosing. So now I'm going to talk about using pairs of TMS pulses and changing the timing between two pulses to probe different types of neuronal receptors. So we have this picture on the left of a single TMS pulse creating a motor evoked potential. But now, if I precede that first pulse, labeled TS here as test stimulus, by 1 to 4 milliseconds by a subthreshold TMS pulse, now the second pulse, the test stimulus, results in a smaller wave, the superimposed red line. And we think the GABA A circuitry is involved. So this paradigm is called SICI, which stands for short interval cortical inhibition. And what we think is happening is that the first subthreshold pulse is activating these superficial axons, and in particular they're activating these axons are firing and they're getting this GABAergic network to respond. Now when the second pulse comes in, it's to an already inhibited cortex, and the overall response to the cortical spinal tract is reduced, resulting in the inhibition we observe in the MEP. So this is an example of using TMS as a biomarker, and basically it's a way we can probe the integrity of the GABAergic circuitry. So in normal controls, you should have some inhibition by the first pulse. You should have your GABAergic system, when activated by TMS, should have a reduced response from the test pulse of 1. But here, this is showing in treatment-resistant depression, they don't have this inhibition. The second pulse, 2 pulses give the same response as a single pulse. And so, but now when depressed patients are giving medication, their responses are normalized to the control levels. And we think the GABA-A circuitry is involved in this because researchers have used, Alf-Zieman's group has used pharmacological methods to block these TMS responses in humans, and also in intracellular recording. So this is a trace of a single cell recording and this is the electrical stimulus, and the glutamatergic receptors are blocked. So all we see here is the inhibitory response, and this first wave represents the GABA-A component, and it's very short latency because the GABA-A receptors are the ionotropic variant of GABA receptors, which are fast-acting, and they allow chloride ions to flow into the cell. Chloride is negative, and that inhibits the cell, resulting in this hyperpolarization here after response. Now, we could change this 1 to 4 millisecond timing between the pulses to a longer interval, 50 to 200 milliseconds. And now we think the GABA-B system is involved. The GABA-B system acts through these slower second messenger pathways that match the kinetics of this 50 to 200 millisecond timing between the pulses. And finally, we could use a medium interval of 10 to 15 milliseconds to probe the NMDA system. And now the second pulse, the pair of 2 pulses results in a larger MEP than the test pulse because the NMDA response is excitatory. And so this is all these intervals are part of a continuum of responses that start by short intervals inhibiting and traversing into facilitatory responses such as an NMDA response as we increase the interval, and then back down way out to 200 milliseconds back to inhibition using the GABA-B system. Okay, so I've got one more slide because I wanted to just include talking about repetitive TMS, because I've usually been so far in this talk just talking about probing the brain with single TMS pulses or at least pairs of pulses, and using that as biomarkers, measures of the response and the integrity of the brain, maybe using it, testing that, how are drugs changing these responses or disease changing these responses. But repetitive TMS is FDA cleared for depression, and you'll see this used in all different parts of the brain and different diseases to try to treat different diseases. And how it works is basically, people say, like, we've applied high-frequency repetitive TMS, like it's a black box, like they've applied a drug or some other intervention. And how it works is you take your baseline. This is an example of using it in motor cortex. We'd have our baseline MEP response. Say we take 25 pulses and get some average wave that's of this amplitude. Give many responses at many TMS pulses at a high frequency for, let's say, there's different protocols. The protocol for depression lasts about 45 minutes. And then afterwards, we, again, use our single pulses and test how big is the MEP now. So after this high-frequency repetitive TMS, the wave is larger. If we use low-frequency TMS, we could actually make the wave smaller. We could create an inhibitory response. And we think this is happening through Hebbian plasticity, which is strengthening or weakening the synapses between a presynaptic activated pathway to the postsynaptic response, to the postsynaptic cell. And it's more complicated than this, because sometimes if your synapses are already very strong and you give a high-frequency train, you might actually see inhibition afterwards. So it's more complicated. This is a good starting framework to enter the literature and understand it better. And this is an example in motor cortex, but you can move out of motor cortex. So for depression, they target the left prefrontal cortex, which is thought to be underfunctioning, and apply high-frequency TMS and try to increase the function. And the baseline and post measures might be, MATTR's depression rating scores or something like that. And that's all I have for now. So I'm going to leave it to Z to take it.
Good afternoon. No reaction, okay. My name is Z. I'm a research fellow in the non-invasive neuromodulation unit, where we study, what else? Non-invasive neuromodulation. That is everything short of surgical implantation of electrodes in the brain, and even those techniques we think pretty hard about. In this lecture series, we focus primarily on transcranial magnetic stimulation because that is becoming a very popular technique these days, not only for clinical treatment, but also for neuroscience research and also for diagnostics. But it didn't start there. The history of transcranial brain stimulation goes back to antiquity. The ancient Egyptians were very well aware of electrical properties of catfish, and they've tried to use these electric-generating fish to treat all kinds of ailments, gout and intractable headache. The Greeks and Roman clinicians actually used torpedo fish like this to numb pain during childbirth. These creatures were considered mythic in Greek mythology because they seemingly have the ability to shock fishermen from a distance without any apparent physical contact. Actually, for the numbing of pain during child labor part, it's not clear that whether or not you need actual physical contact with the torpedo fish. I think they just need to be in the room. Actually, if you are going to try this at home, you have to do this right. So you have to actually trap the fish when the moon is a sign of the Libra. And then you have to keep the fish open for 3 days. That will give you the best effect. I wish I was making that up. I really wish I was making that up. It wasn't until the late 1700s, though, when people started to look at animal electricity in a more scientific way. People like Alessandro Volta, people like Galvani. Actually, the scientific debate between Volta and Galvani not only spawned the whole field of electrophysiology, but inspired much of electromagnetics, electrochemistry, and not to mention the invention of the electric battery. And it was the nephew of Galvani, Giovanni Aldini, who later became a physics professor in Italy. He actually tried transcranial electrical stimulation in humans. He was trying to treat a 27-year-old farmer with melancholy madness, which is your modern-day major depression. To administer the treatment correctly, Aldini actually tried the electrical stimulation on himself first, and he apparently reported that he felt a great shock to his skull, which rattled the inner fluids of his brain, and then he became insomniac for days. Now, that might have been his side effect and his experience with transcranial electrical stimulation, but his patient, who was suffering from depression, reportedly was cured of depression after weeks of this electrical stimulation. Unfortunately, Aldini's work was overshadowed by some of his other more unorthodox scientific experiments. Aldini was famous for doing these public demonstrations of galvanized corpses, that is, using electricity to try to reanimate dead bodies, which later inspired Mary Shelley's Gothic novel, Frankenstein, or Frankenstein, if you're familiar with the movie. Fast forward to the mid-1800s, we have actually devices that you can buy for home use. And these miracle devices can treat everything. Anything from apparent death to change of life to falling of the womb. There's a treatment for that using electrical stimulation. Fast forward to the 1930s, we have the invention of ECT, electroconvulsive therapy. Now, there are a lot of problems with ECT and its side effects and so on. and I don't have time to go into the history of ECT. Needless to say, it inspired the invention of other forms of transcranial brain stimulation. And by 1985, we have the first human TMS device developed, generally credited to Tony Barker and Reza Jelinek and colleagues. The physics of TMS is nothing more than electromagnetic induction, the same phenomenon that you probably study in high school physics. You take a permanent magnet or an electromagnet in this case, and you move it around really, really fast in a spool of wire, right? And that would generate a current flow in the secondary windings, which you can measure. So in this picture, just imagine that you replace this liquid battery on the far right with a TMS stimulator and replace that mini coil A with a TMS coil and replace that spool of wire B with the head, and you have TMS. Actually, there's something wrong with what I just said. The problem is that the head is not a spool of wire. Think about that. Actually, TMS on human tissue is an incredibly inefficient process. The head and tissue in general is not a good it does not couple to magnetic fields very well. And that has a lot of repercussions when it comes to device design, because you do need to have so much more of a powerful source to induce just a tiny current flow in the brain. If you were to open up a TMS device, this is what you're looking at. That can on the bottom right is the capacitor, which gets charged up to about 2,000 volts. All of that charge is dumped to a TMS coil, generating a peak coil current of 7,000 amps, creating a surface magnetic field up to 2 Tesla, and it only creates about 1 volt per centimeter electric field in the brain. I know some of you don't have any sense of what these numbers mean, so let me give you a little bit of scale. This is the HMS Dreadnought class battleship commissioned by the Royal Navy in around 1906. This battleship actually has 2 revolutionary features. The first feature is that it mounts the biggest guns that the world has ever seen. The second feature is it's powered by a steam turbine propulsion system, which is designed to output about 23,000 shaft horsepower, which is about 17,000 kilowatts. That's about how much power TMS uses. Impressive, isn't it? Think about that the next time you fire a TMS pulse next to a person's head. Yeah? And design of the device is really difficult because of these high power and high voltage, high current requirements. Some of the first generation TMS devices, including the ones that are still commercially available today, are very simple circuit topology. Basically, it's just an RC circuit or RLC circuit. The circuit that you see on the top is the first generation TMS device. You charge up the capacitor. All of that charge is dumped to the inductor, which is the TMS coil, and that creates a sinusoidal waveform, an overdamped sinusoidal waveform that you see on the right, that what we called a monophasic waveform, because it's predominantly unidirectional, and this happens because of that overdamped feature of the waveform caused by the ohmic loss from that resistor in the middle, R. Such topography is not very efficient for repetitive applications of TMS because every time you fire a pulse, you increase the ohmic heating on that resistor, and it would overheat the device very, very quickly. A more efficient design is that you get rid of that resistor, put it in a pair of anti-parallel diodes that allows the current to flow back to the resistor and charge that back up, and so that you can use the energy for the next pulse. And with this circuit topology, you have what's known as the biphasic pulse, or you can let it ring and have a polyphasic pulse like that. And these devices, again, are what's commercially available today. Here at the NIH, we recently bought a new device, and this is the so-called controllable pulse width TMS device. Now, it turns out that neurons in the brain much prefer rectangular pulses. They really don't like to see sinusoidal pulses as a way to modulate their membrane potential. And so about 10 years ago now, Engel Peterchev, back then was from Colombia, invented a device that would produce near rectangular pulses by using these high-power switches that sharply cuts off the coil current, and that would provide these very, very fast transient electric field pulses. So we have a device here at the NIH, and it is the first commercial device of this type in North America. So we are actively seeking collaborators to play around with this. So if you have ideas, please come talk to us about it. This device is not out yet, but it's I think it's currently being researched, and this is invented by my colleague Stefan Gutz, the so-called modular synthesizer. If you break down the circuit into smaller modules, you can build each module with cheaper parts. You can have many modules that would allow you to control in a very fine-tuned scale the current levels, and with infinite number of modules, it would allow you to basically create any arbitrary current waveform in TMS coil. Again, it's not out yet. It's probably going to take us a couple more years before we have this device. So I've talked about the temporal aspect of TMS. Now let's go to the other important issue, which is the spatial aspect of TMS. But there are some rules that you guys need to be aware of before we go on to talking about electric fields and coil designs. With TMS, there's no 3D focusing in depth. So it is not possible to create a three-dimensional focus of the electric field in depth. If you want to use TMS to stimulate the deep brain region directly, that is not possible. The second rule is that conventional TMS coils, such as the figure-8 coil, has relatively low penetration depth, up to about 2 or 3 centimeters from the surface of the head, hitting at right about the gray matter, white matter boundary. Okay, you can use a bigger coil, and then that can stimulate a little deeper, but not too deep. Yeah, the electric field, as you can see on the right-hand figure, is always maximum at the surface of the head and surface of the cortex, and then it sort of decays exponentially as you go towards the center of the brain. Now, you don't need to use a figure-8 coil. In fact, there are many coil designs. There are this many. Several years ago, I wrote a paper trying to collect all of the TMS coil designs in the literature. It's kind of a hobby of mine. You might have other hobbies, like collecting stamps or friendship. Mine is collecting TMS coils, all right? So I collected about, back in 2013, when I published this paper, I had about 50 coils. Now I have, that number has gone up to about 60, 70 coils. And I loosely categorized them into 3 categories, loosely, okay? That's the upper, okay, so the first type of coil is what I call circular type, and this is one of the first TMS coils are circular type coils because of ease of construction. You just take a post and you wrap wires around it, right? And it produces an electric field distribution on the head that is circular, right? So you can see on the bottom, and these are electric field simulations using finite element methods on a spherical representation of the head. And you can see here on the bottom that all of these coil designs produce a circular loop of current flow underneath the coil. You can see also here that there are some coils that has weird geometry. These are so-called H coils. They also belong to this family of circular type coils, and you can see what their electric field distribution is like. The second type of coil, of course, is the figure-8 coil, which is now becoming the most popular TMS coil. And you have 2 windings next to each other, and you have a peak electric field underneath the center of the coil where the two windings join. And you can see here that there are a variety of figure-8 coil designs, some of them that don't even look like a figure-8, but still produces a figure-8 pattern. The third type, I couldn't sort them into circular or figure-8. These coils have multiple turns, multiple loops. And you'll see later that they actually belong to one class or the other. Now, here I plotted all of the coils in focality and depth. So on the x-axis is the depth of stimulation using these 60 coil designs. And on the y-axis is the spread or the tangential extent of the electric field. It's a measure of focality. The higher the spread, the more non-focal is the electric field, okay? So you can see here all of 60 coils plotted into this focality depth profile. And you notice a couple of features that are quite interesting. Notice that there are two lines. The top line are where all the circular coils lie, and the bottom line is where all the figure-8 coils lie. What does that mean? That means that figure-8 coils are intrinsically more focal compared to circular coils. That is, for the same depth of stimulation, you stimulate less brain with figure-8 coil. Observation number 1. Observation number 2, notice that these two lines are trending upward. That is, the deeper you try to stimulate, it's necessary that you also stimulate more brain. It's the second rule. So that's the fundamental trade-off in TMS, what we call the depth focality trade-off. Third observation, notice that there are no coils out in the right lower corner. That's when you can stimulate really deep and stimulate very little brain, right? We don't seem to have a coil geometry that can achieve a focal deep stimulation, at least not at these frequencies with TMS. Final observation, notice the two lines converge to coil 0. What is coil 0? Anybody? It's what we called the flux ball. If you look at the bottom right there, it's when you wrap your own head with wire, all of it. Now, I'm not saying you should try it, right? But it is the limit with TMS in terms of depth and focality. This is a pretty nice figure that somebody should make it into like a T-shirt or something. I have these for sale after the lecture if you are interested. I'm kidding. Okay, so for the last few minutes, I just would like to say a few words about the use of TMS with concurrent neuroimaging techniques, since this is a fMRI course, so I would like to cover a little bit of that. And just say a few words about technical challenges and safety aspects of combining TMS with various forms of neuroimaging. The first modality is PET or SPECT. You can do it it can combine very well with TMS. Actually has a number of nice features that the TMS pulse don't need to be in sync with the scanning procedure. So this allows you a little bit more flexibility in terms of timing of the relative timing of the stimulation and the scanning. The magnetic field produced by TMS also does not interact with photon emission, so you don't have to worry about noises and so on. Probably the only thing you have to worry about is electrical artifact or potential damage of the photomultipliers in the PET scanner by the TMS coil. So you might want to do some metal shielding for your photomultipliers. But these two techniques are very nicely combined. SPECT is not often done simultaneous with TMS because of the long scan time. So that has been done exclusively for offline applications. That is, you do TMS before or after, SPECT before and after a stimulation session. The second techniques that we do a lot these days is combining TMS with EEG recording. Some of the safety aspects you have to worry about is electroheating. So the geometry of the EEG recording electrode is very important. You don't want to have closed ring electrodes underneath the TMS coil. because those will pick up flux and would heat up if you were to do a repetitive stimulation. So what you do is you take these ring EEG electrodes and you cut a slot in it. This way you reduce the inductive loop area, thus minimizing heating and inductive current flow. Second feature is that you would want to try to minimize inductive loops that are formed by the wires that are coming out of the EEG electrodes and that goes through the amplifiers. You might want to have them bundled up, unlike what's displayed on this picture here. The third thing that you have to be aware of is that the amplifiers need to be sort of specially designed because of the TMS pulses create very large magnitude artifacts and they can potentially saturate the amplifiers. So ways to handle that, you can have sample and hold circuits in the amplifier. Basically, right before you deliver a TMS pulse, you latch onto the signal and then you pin it. And then right after you deliver the TMS pulse, you allow the signal to record again, and that will take care of the TMS artifact. Or you could have an amplifier with a very slow slew rate, so it doesn't respond to very fast, transient, big magnitude pulses. Or you can have an amplifier with a wide dynamic range, so it won't saturate. So all of those techniques are considered in a specially designed amplifier for TMS applications. TMS with optical imaging, like fNIRS or event-related optical imaging, has a lot of potential because the imaging equipment is kind of portable and you can just put them on the head and do TMS over it. Again, there's no interaction between the magnetic field and any of the optical sensing. The only thing you have to be aware of is that if you were to do sort of optical imaging directly underneath a TMS coil, you have to make sure that your optical probes have a very thin profile because that would add distance between the TMS coil and the head. And considering how fast the TMS electric field drops off with distance, you're going to need to account for loss of signal there. I think that's the only thing that you have to worry about with this kind of modality. Last but not least, TMS combined with fMRI, there are a lot of technical challenges in combining these. I'll just name a few. The first thing has to do with the forces that are induced on the TMS coil because of the large static magnetic field in the scanner. And so to cancel out the forces, you need to use planar figure-8 coils. So no coils that are angled, no circular coils because the torque will tear apart the coil. All right. To minimize the forces, use biphasic pulses as well. And also the stimulator electronic control, the device, the capacitor charging and discharging, that can generate a lot of RF artifacts in your scans. So if you are to have the stimulator in the scanner room, shield it. Better yet, move it outside of the scanner room and pass the TMS coil cable through a waveguide. And again, shield everything, right? The only problem with that is the stimulator being so far away that you're going to need to use a longer cable, and that introduces additional resistive and inductive losses. You change the inductance of the coil even. And so in that case, to compensate for that, you might want to use a thicker cable or parallel cables or something else, right? Or increase your stimulator output to compensate for signal loss. Sound is critical in TMS fMRI because of reverberation inside the scanner. When you fire a TMS coil, there's a very loud clicking sound, and so hearing protection, unlike this subject here, is very important. Final technique I want to touch on, and this is not done in humans yet. It's TMS combined with neural recording. And we managed to work this out several years ago at Duke, where we have the first system to do single unit recording, simultaneous simultaneous with the TMS stimulation, and in a alert monkey, awake behaving alert monkey. So I designed the coil to fit around the recording chamber, and you can see here that on the right-hand panel, the firing frequency of a neuron captured. When you apply active TMS, the firing frequency is increased relative to sham stimulation. It's a good platform if you want to really understand the cellular mechanism of TMS, something that you cannot do so well in humans or smaller rodent animal models of TMS. We're winding down here, but I just wanted to show you this slide. We haven't talked about any of the other stimulation modalities beyond TMS in this mini lecture, but we do study all of them, and one of my goals is to show you where they are in a electric field continuum, compare scales in terms of how strongly they stimulate the brain. TMS is suprathreshold, so it's got one of the strongest electric field induced in the brain. Nowadays, the subthreshold stimulation paradigms are becoming more popular now. Things like transcranial direct current stimulation, things like spinning magnets, right? And those produce orders of magnitude smaller electric field. And yet, various studies have shown that those techniques have somewhat of a neuromodulatory effect. And that's it for my talk. And I thank you for coming on a Friday afternoon, and we're ready to take questions. Yes, ma'am. Could you use the microphone here up front? This is being recorded for prosperity. Yeah. So don't be alarmed that people will be watching this over and over again and stays up on the internet forever and ever, long after we're dead.
That was actually just a kind of a silly question, but in terms of the saturation of the amplifier, I mean, and so in some studies, just let the amplifier saturate, no problem, it just kind of saturates. Why is that such a technical issue?
Yes.
It takes a long time for it to recover from the saturation?
Exactly. So the question, I don't know if the microphone is working, is with the issue of amplifier saturation. Some experiments allow they let the amplifier saturate and let it be. Why is that an issue? Yeah, the issue is with signal recovery. Sometimes it takes a while for the signal to recover back to baseline or something comparable to baseline. With TMS EEG, that recovery, even if it's tens of milliseconds, that's already too long. The signal already have traveled across to the other hemisphere, and you're not studying the local effect. So we need better amplifiers that can recover much faster, or have other strategies that can deal with this transient, long exponential decay of the amplifier. Well, if there are no other questions, we're off the hook. Thank you.